Hi there, class. Welcome to another acid-base lecture. And in this lecture, we are going to take an extensive look at buffers, which is going to introduce the Henderson Hasselbalch equation, which will be one of the equations that we heavily rely on when we're doing titrations, because we can link it to the pKa of an acid and determine pH if we know the concentration of our acid and conjugate base. So that's going to be the primary focus of this lesson here. We will have one additional acid-base session after this, and that's going to be for titrations. So I should have that uploaded within about 48 hours of this lecture, and that will conclude the acid-base material for this specific section, and then we will move on to some other types of equilibrium constants. Specifically, we'll start looking at KSP, which deals with solubility and whether a product will form a precipitate or not. So that's where we're going to be headed after this. So let's get started with the acid and base buffers. So to start off, let's actually discuss what a buffer is. So a buffer is going to be a solution. It's a weak acid or a weak base and its respective conjugate. So you may hear me referring to acid over and over again, but you could certainly have a buffer that is a weak base with its conjugate acid. Okay, but when you have those two conjugates together in a solution, it's known as a buffer. And one of the things that makes a good buffer is we usually attempt to keep a 1-to-1 ratio as far as moles, concentration, however you want to look at it, for the weak acid and its conjugate. So buffers are going to be useful when you want to stay in a specific pH range. So when we utilize buffers, the goal of a buffer is that it can take somewhat of a mild beating from either an acid or a base, and it will allow the solution to stay within the desired pH range, give or take maybe 1/10 of a unit, but it's not going to have drastic fluctuations like you would in a non-buffered solution. All right, so how do buffers work? They work by establishing an equilibrium between the acid and the base. So we pick out the equal amounts of conjugate acid and conjugate base, and an equilibrium, a Ka or Kb, depending on what we're working with, will be established there. Right? And then what happens is when hydronium or hydroxide is introduced from some outside source, it's going to disturb the equilibrium, and the conjugate pair will work through Le Chatelier's principle in order to reestablish the equilibrium. So you've got this conjugate acid and base that are working together, and then as soon as hydroxide or hydronium comes into the solution, it's going to disturb the equilibrium, and the conjugate acid-base pair will work together in order to reestablish that equilibrium. Okay, so as a result, the addition of an acid or a base to the solution is going to have a negligible effect on the pH as it reestablishes itself. So it will have some effect, but it's going to be very small as long as we're staying what's known in the buffer region. Okay, so this is a good way to visualize buffers. So what we have, and the example I'm going to work with later for math, is acetic acid. This tends to be a very common acid to work with when starting to teach buffers as well as pH. It's a monoprotic acid. It's a very common organic chemistry reagent. So you can see the equation here states that acetic acid in water is going to go to the hydronium and the acetate ion. So what would happen if I had equal amounts of acetate ion and the actual acetic acid sitting in my buffer? Well, you can see in each case, if some acid were to be added, if H3O plus was added, the equilibrium position is going to shift to the left because I've added some acid, which is going to be a product, and it'll get rid of some of that acid through Le Chatelier's principle by attempting to move some of it over to acetic acid. So what happens is, you would expect when you drop the acid in that the pH would go much lower. Okay. However, because some of that acid will be converted through Le Chatelier's principle over into the water and the acetic acid, it's going to decrease the H3O plus concentration a bit, and in return, the pH is not going to take such a large hit when that acid is introduced. Now, the opposite is also true. if a hydroxide ion is going to be added, the equilibrium position will have to shift to the right, because a hydroxide ion is going to eat up or remove the H3O plus, right? If I drop hydroxide in, it's going to react with H3O plus to give water. So if that's the case, and I'm creating water, and I'm creating acetic acid from the acetate ion, then that means I'm removing some of these. So obviously it's going to shift in this direction to replace or replenish some of the hydronium ion. So what would you expect with a base? You add a base into the solution, and you would expect the pH to go up. And it turns out it doesn't go up quite as much as you might think, because as we add the OH, it removes some of the products, and so Le Chatelier's principle shifts and creates some more hydronium, bringing the pH back down to a closer level to where we initially saw it. Okay, so this is the concept of buffers. We have the equal amounts of the conjugate acid and the base, and they're working together to maintain equilibrium, or Le Chatelier's principle, if they become disturbed. And you can see through this visualization, and I've got another one right here, these come out of the OpenStax book, that you're starting in the middle here. If you add acid, you're going to deplete some of your base, and you're going to increase a small amount of your acid. But in general, it will try to keep that hydronium relatively stable until you get to a point where you overwhelm the buffer, and that can certainly happen. So that's what we're going to talk about here next, is when you overwhelm the buffer. Okay, so since buffers are based on molar conjugate ratios, the 1-to-1, the introduction of exogenous, which means outside or not native to the reaction, the introduction of exogenous acids and bases will deplete one of the species. So if I'm adding acid, it's going to deplete that conjugate base and form more acetic acid. And if I add that base, it's going to require some of the acetic acid to be used up and create more of the conjugate. Okay? So we're going back and forth. Again, if I go back one slide here, you can see one starts to slowly pile up as the other one starts to decrease. Okay? So a buffer will generally be effective at maintaining the relative pH range, and it's usually about within 1 pH unit, okay, until the conjugate is less than 10% of the molar amount of the other. So that is to say, in this example here, we have equal amounts of the acetic acid and the acetate ion. If at some point one of these becomes less than 10% of the other, meaning that ratio there, you start to go past the 9-to-1 ratio of the way that they would look, then at that point, your buffer is going to become overwhelmed, and suddenly small amounts of acid or base being added can all of a sudden lead to these wild fluctuations in pH. So buffers have an effectiveness, but their range is going to be limited because you can use up or chew up through a lot of your material on one end or the other. Okay? So you can see this is a visual representation here of when you start to collapse in terms of your buffering region. And this was something you were asked to do in your lab, was to circle the buffering region. So you've got this sort of flat area before you take a jump, right, as you start to head to your equivalence point. And this flattened out area is known as the buffering region. This is where you get some buffering capacity. So let's take a look here, okay, this buffer. So this is again for acetic acid, and we're adding NaOH to the acetic acid slowly. So we start out, and we're at about a pH of, it looks like 4.7 or around there. Okay, and then we can add 10, 20, 30, 40. Okay, so I add 40 milliliters, and it looks like the pH is maybe 5.1. So we went from 4.7 to 5.1. That's not a horrible increase, okay? It's certainly, depending on the system and how delicate it is, it might be considered a big increase, but that's pretty good for adding 40 milliliters of base. But then look what happens as I start to deplete my acid, my acetic acid reserves. Now, as I go from 40 to 60, okay, it's going to go from about 5.1 close to 5.5. So what we just took about 40 milliliters to do, the next 20 milliliters did that, okay? And then what happens as I go from 60 to 80 if I do another 20 milliliters? Well, now I'm looking like I'm approaching a pH of 6. And so what you're going to see is, right, as we go from 80 to 100, Well, at 100, we're almost at a pH of 7 now. So at 80 milliliters added, we are at a pH of, and this is approximate, I'm going to say 5.8, 5.7, somewhere around there. And then another 20 milliliters brings us up to 7. So you're going over a pH jump in 20 milliliters, whereas the first 40 milliliters, we only had about half of a pH jump, if that. Okay? So again, it's going to, as you start to approach this 10% of the other conjugate, you're going to have a collapse in the buffering capacity, and all of a sudden the acid or base that's being added is going to be like a runaway train in terms of the pH level. All right, so this right here, and we're going to see this as we work through the math, this is the Henderson Hasselbalch equation. It is actually derived from Ka, so if you were to rearrange this, you could make it Ka equals, and then you could have the hydronium and the conjugate base at the top divided by the HA at the bottom. All right. Now, the way that this got rearranged is through some logarithmic transformations and isolating the hydronium, and this is what we end up with. It's a very useful equation to tie pH over to pKa with the concentration of your acid and your base. So what we're going to do is go ahead and move into some calculations here. I want to work through two calculations. One of them will just be finding the pH of a buffer, and then the other will be, once we've added some acid and or base to that buffer, what is the expected change in pH based on that? All right, so we're going to take a look at that. Okay, so here's the whiteboard for the acid-base buffer problems. So the first problem says calculate the pH of a buffer solution that is 0.100 molarity acetic acid and 0.100 molarity sodium acetate. So keep in mind, when it says sodium acetate, sodium is just the cation form that you would put in for the acetate ion, because when we have ions, they usually don't exist in free forms. We have to bundle them up as salts in order to measure them out in a lab. So let's start with the general equation here. We have acetic acid, and acetic acid is aqueous, so we're going to put it AQ with water. And this buffer will be in equilibrium here. Its acetic acid is going to have the H3O plus on the product side, as well as its conjugate, which is the acetate ion. Okay, now what I'm going to do here, there's a couple ways that we can solve this. I'm going to start with the traditional ice chart. We're going to go through it, and then I'm going to show you how you can use the Henderson Hasselbalch equation to save you some time, but it's important that we're practicing both of these. All right, so the initial here is going to be 0.100. All right, now in most of these other examples that we've come across so far, we have the initial acid and then it dissociates, so these are both 0. But in this case, they're not, because while the hydronium is 0, I'm being told that I'm adding a certain amount of conjugate base right from the start in the solution. So this is going to be 0.100 as well. All right, now the change here, this is monoprotic, so it's all single x's, so it's minus x plus x plus x. And then we end up with the actual equilibrium variables. So the acetic acid is going to be 0.100 minus x. The hydronium will just be x. And then the acetate, this is something new that we're not as used to seeing yet, is going to be 0.100 plus x. So when I have this, I can now set this equal to the Ka. The problem didn't give a Ka, so what I want the class to get used to doing is going in and picking these out from charts. So sometimes I may include it to save you time, okay, but what I'm going to do here is just bring up the chart, and the first one here, okay, this is in your OpenStax book. It is, I believe, Appendix H. But if you come down, you will see the ionization constants for weak acids, and here's acetic acid that we're working with. It says 1.8 times 10 to the negative fifth. So that's the value that we'll utilize in this problem. Okay, so let's continue here. we're going to set 1.8 times 10 to the negative fifth equal to, now I have to draw out the equilibrium constant. So it's going to be the products. I have x, and I also have 0.100 plus x over 0.100 minus x. Okay. Now, for those of you that really would like to do that, you can solve the quadratic equation. I prefer to save myself time, so the method I'm going to use is the 5% rule. Now, what I want to do first is factor. So the x is going to go to here as well as here. So let's rewrite what we would have here. Okay, we would have 0.100x plus x squared. Okay, and then the bottom we would have 0.100 minus x. So the general assumption is that x is going to be very tiny. So what x's can I get rid of here? Well, 0.1, if I'm saying x is very tiny, then 0.1 minus x should just give me 0.1 because I'm taking a very small value from it, so I can get rid of that one. And then if I come up here, the question is, can I get rid of x squared, and should I get rid of this x? So for x squared, if I take a very small value and I square it, it gets even smaller. So if I have a large value over here, and I'm adding a small value that became even smaller, then no, I can get rid of that. I shouldn't need that. Okay, now what about this x right here? Well, first of all, we're going to need to solve for x, so we have to have an x left. Okay, but second of all, anytime you have a number, you need to realize that multiplication and division of a small number with that number could end up drastically changing it. Okay, so to give you a general example, if I have 1,000,000 and then I say x is very small, so let's say that x is 0.5, that's very small compared to 1,000,000. Well, if I take 1,000,000 times 0.5, I end up with 500,000. That's a very drastic change. Then saying, let's take 1,000,000 plus 0.5, which becomes 1,000,000.5. That's rounded, just going to be about 1,000,000 or 1,000,001. So you don't have much difference there, whereas the other one cuts the value directly in half. So if you see x's that are being multiplied or divided, your 5% rule is not going to allow you to drop those. You need to keep them in. But if you see them added or subtracted, you should be able to ditch them, provided the 5% rule holds up. So this makes for some simpler math, because I now have 0.1x over 0.1. These values can drop out, and then I find that x is simply going to be equal to the Ka. So that makes my life pretty easy. Now the thing that's good here is that x is a pretty small value, times 10 to the minus fifth, whereas my initial concentration is 0.1. So I do want to check just to make sure, but if I'm eyeballing that, I would say I'm going to be okay. Okay, so it's going to be 1.8 times 10 to the minus 5 over 0.1. Okay, and this is the initial, remember it's the initial concentration of the acid, which we have up here. And that's times 100, because we're looking for a percent here. And it turns out that if you solve that, you're going to get 0.018%. All right, so that right there is going to be a pass on the 5% rule, because we're nowhere close to 5%. So what we can do now is we can utilize this and say, all right, x is going to be 1.8 times 10 to the minus fifth. So here is H3O plus. It's going to be 1.8 times 10 to the minus fifth because it's x at equilibrium. So let's go all the way back and look at what the question asks. It says calculate the pH of a buffer solution that is 0.1 molarity acetic acid and 0.1 molarity sodium acetate. So the pH, we now have the hydronium concentration, right? And all I need to do to find the pH is take the negative log of that. So pH is going to be equal to negative log of x, and x was determined to be 1.8 times 10 to the minus fifth. Okay, now keep in mind there's two sig figs here, so I need to end up with 2 decimal points in my pH, and if I solve for it, I find that the pH is going to be equal to 4.74, and that is my answer. All right. So traditional method, we can still find the answer here. But now let's take a look at the new equation. We're going to use the Henderson Hasselbalch equation and show how it can save us some time in a situation like this. So what I'm going to do is I'm going to say Henderson Hasselbalch says that the pH is equal to the pKa, right, which is going to be plus the log of, now in this case I know what it actually is, so it's going to be the log of the conjugate base, which is the acetate ion, over the acetic acid. Okay. So in a case like this, now if you needed your pKa, you would have to take the negative log of your Ka, and you could plug it in there. All right, but what I want to show you here is that this right here is very important, the logarithmic part, because especially when you have equal amounts, we're taking the log of 0.100 and the log of 0.100. So that's going to come out to be 1. And the log base 10 of 1 is equal to 0. So what I'm going to say here is that the pH is going to equal the pKa plus 0. So anything plus 0 means that the pH is equal to the pKa. Okay, and this will always be the case when you have equal stoichiometric amounts of conjugate acid and conjugate base. When their concentrations are equal, you're going to have the pH equal to the pKa. So what I can do here is say, what is the pKa? Well, we already did this. The Ka is 1.8 times 10 to the negative fifth, which just so happened to also be the hydronium concentration, right? So if I take the Ka, okay, and I turn it into pKa by taking the negative log of this, well, we can just save ourselves some time. We already took the negative log, right? So instead of it being pH this time, we're just calling this Ka, and it's going to become pKa after that transformation, and there you go. The pH is equal to the pKa, right? So I have one more problem, and we're going to test out the Henderson Hasselbalch equation here, but it's going to involve quite a bit of math, so you need to pay attention here, because now we're going to mess with our buffer. So the first problem, we just simply set up the buffer and said, all right, now I want to know what the pH of my buffer is. That was easy enough. But now we're going to mess with that buffer by adding some base to it, and we got to figure out what's going to happen. All right, so it says, what would be the pH of the buffer after adding 1 milliliter of 1 molarity NaOH? So I want you to pause for 1 second, okay? And actually, hold on, I left an important part out here. What would be the pH of the buffer after adding 1 milliliter of the 1 molarity NaOH? And we're assuming that there is, I should have added this in, I'm very sorry, 100 milliliters of buffer. You're going to need to know that for a final volume later. All right, so when we take a look at this, we want to think. So first of all, the pH, okay, of the initial buffer was 4.74. So if we add NaOH, we should expect that the pH is going to go up. Now we're only adding 1 milliliter of it, so we're probably not going to go through all of our conjugate acid-base system. So I would expect that it'll probably still be somewhere in the 4 region, but it should go up a little bit, right? So the next thing we need to think about is, how is this going to affect the equilibrium if I'm adding the hydroxide? Well, when I add hydroxide, it's going to react with the acid that is present, and the acid that's present here is acetic acid. Okay, so as I use up the NaOH, okay, as I add NaOH to solution, it's going to remove acetic acid from the solution. And when it removes the acetic acid from solution, it's the OH is going to come and remove this H, right? So it's also going to add or generate acetate ion, we have to keep all these steps, all of this logic here. As I add the NaOH to the solution, it will deplete or remove acetic acid, which will generate and create acetate ion. So what I'm really going to do here is I'm going to screw with this ratio, right? Because they're not going to be equal anymore. As I remove one and start generating the other, this is no longer going to be 0.1 and 0.1. I'm going to have different values there. And that means that I'm going to have a different value than 0. So that value will be added to the pKa, and I will expect to see the pH go up by some amount. So the question is, what is that amount? We have to find it. All right, so let's get started here. The first thing we want is to find the actual amount of NaOH that was added on a molar basis. So we've got 1 molarity, and we added 1 milliliter of it. So I'm going to convert that to liters. Okay, and this will give me moles of the NaOH. So this is going to be 0.00100 moles, all right, because 1 times anything is itself, of NaOH. So that's the amount of NaOH that was added. Now, the next thing that I want, okay, and let's mark this just so we know what we're talking about. This is the initial NaOH that was added. Okay. So now what I want to do is find the initial amount of acetic acid in moles, okay? Because what I do know is that acetic acid is monoprotic and NaOH is monobasic, so they will react in a 1-to-1 ratio to create the acetate ion. So I can basically take the amount of NaOH that's added and assume that's how many moles of the acetic acid will be used up. So we'll get there in 1 second. Okay, so the initial acetic acid is going to be 0.100. This is coming from the first problem, right? So if I go all the way back up, this was the concentration that was given. We're still working with this buffer. Okay, and then I'm going to multiply it by the 100 mils, right? That's the part that I meant to put in there. So I have 100 mils of it. And if that's the case, then when I do this, I should end up with 0, hang on a second, 100.0 mils. Okay, so I should end up, that's liters, with 0.0100 moles of this, the acetic acid. And I will note that it is also the same exact amount for the acetate ion, because the acetate ion had the same starting concentration and it is also in the same volume. All right, so the next thing we want to do is determine the loss of the acetic acid. All right, so with loss of acetic acid, we need to take the initial amount of acetic acid, 0 moles, and from that we are going to take the NaOH amount. So this is how much is going to be lost, okay? Because we have some initial amount of acetic acid, and then it loses the moles of NaOH, because that's how many moles of acetic acid would be depleted. So 0.00100. Okay, this is the loss of acetic acid, and that's going to give us how much acetic acid remains. And so the amount that remains in solution would be this many moles. Okay. All right, so now the next thing we need is the gain of acetate. So how much acetate did we form once we lost that acetic acid? Well, the ratio, the balanced equation for acetate to acetic acid is also 1-to-1. So that means that I have the initial amount of acetate And then from that, I'm going to add the same amount that was lost for the acetic acid, because it all gets converted into acetate. Okay, so this is going to equal 0.0110 moles. And this is how much remains, right? You could say how much has been added total, and this is how much remains here. So these are the values we actually want to utilize after we convert them into molarity. So that's the next step. Let's put these into molarity. Okay, so for the molarity, because we're going to need concentrations for Henderson Hasselbalch, the molarity of the acetic acid is going to be 0.0090. That's the moles that we determined would be remaining in solution. Right, over the total volume. Now the total volume is 100 milliliters of buffer and 1 milliliter, right, of the 1 milliliter of the NaOH that was added, for a total of 101. Okay, so if we solve for that, we're going to find, okay, 2 sig figs, because there's only 2 of them up here. We're doing multiplication division now, not addition subtraction. Oops, one too many zeros. 0.089 molarity. All right, and then if I want the molarity of the acetate, I'm going to have 0.0110 moles over, again, same volume. All right, and that is going to equal 0.109. Again, 3 sig figs here, so you can keep 3 in your answer. And that's the molarity of the acetate that we have. So now, what we're going to do is bring the Henderson Hasselbalch equation back. So I'm going to delete just what we have up here in order to work with that. All right, and we're closing in here, so it's going to be pH is equal to the pKa, which I'm just going to write because we found it out. It was 4.74 from the first problem, plus the log of, okay, the base, which is the acetate, so that's going to be 0.109 over 0.089, and that is the value for the acid, the acetic acid. Okay, so when we add this and you solve for it, if you put all of this into your calculator, you're going to find that the pH is equal to 4.82. And there is our answer. Okay, so by adding 1 milliliter of the 1 molarity NaOH to 100 milliliters of this buffer system, the pH goes from 4.74 to 4.82. So I am definitely going to cut it off there because this lecture has gone over half an hour. But buffers, you have to be able to do this sort of math. This is very complex math. So we will practice some more of this in class. But like I said, I want to end it here. You can rewatch this if you need, again, for help. And titrations will be the last thing on the agenda for acid base. So thank you for your attention. Continue watching these videos, learning at your own pace, and I will see everybody in the next one.